I don't know. Até no Archive, eles estão, se vocês procurarem do PI, muitos dos resultados que eu vi são associados a, tipo, mudança de páginas que não, tipo, o formalismo, né? Você fica notar, o formalismo ainda é, tipo, filtrava.
All right, shall we? So finally, we are now going to discuss the 2PI approach to this open Dicke model. So let's say the first part of the, let's say the bosonic part of the action you've already seen, right? And now, again, let me maybe reiterate it, right? Using Martin transformation. Which is gamma I. We get following finger conditions. Action. And so what do we have? First of all, something simple and innocent. The bosonic part. This is now say, and like the losses will be in there. Then we have the say the quadratic part of the diorama, right? So again, instead of, yeah, I think I should explain this. So let me first like one. Okay, so I think this part is pretty clear, right? It's just it just comes from sigma z, right? So if you map sigma z, you of course have something like, you know, eta x, eta y, right? With the right sign, all that. And then you have this part, and you may notice that it is very similar to this part, right? So the time derivative term is very similar to the bosonic one. And this essentially, again, this stems from just the coherent state path integral construction, right? It's, let's say it's, this part is very, very common feature of coherent state path integrals, right? So now it's because like instead of, so now we use so-called thermionic coherent states, right? So for the construction, so, but they are very similar to, let's say, the bosonic ones. But you also have like the overlap, right? Just let's say not trivial. And I think it would be something like, I guess. But I mean, check it. Something like this, right? And from this, because the overlap would be from I, the I plus, I plus, and you already see the origin of time derivative here, right? So that's sort of like it's the same for bosonic degrees of freedom here, right? So this is where this so-called Berry phase term comes from.
So just a technical question. Eta alpha, you are just summing overall, it's Einstein summation.
Yes. So it's the Einstein convention.
Okay, just to clarify.
Yes. Thank you. Yes. Okay, and also some of you probably know this, but these are not your ordinary numbers, but there's the so-called Grassmann numbers, right? Which have this property that eta prime is minus eta prime eta, or this zero. That's all you need to know. They are not your ordinary numbers, but special numbers. That's about it. All right. So this is this part, right? Then you have the interaction term. Interaction term, right? And finally, the loss term. But this you've already seen in Javier's lecture, and let's say as like a two-body loss version, you have also seen in the during the tutorial session, right? So this is something that you should be familiar with by now. All right, so this is our Schwinger-Kelvin section.
Okay, again, sorry, but we had the Hamiltonian of the Dicke model.
Yes.
And then we made the Martin transformation.
Yes.
And then we need to do a Legendre transformation to go to the Lagrange.
No.
No, you just
Well, yeah, I mean, yes, but you know,
just to clarify,
so okay, let me
the steps behind.
sort of the in principle, sort of yes. Let's say for coherent state path integrals. So for coherent state path integral formulation, the action basically takes the form. Let's say the Lagrangian is of this form. Say I. Right, and likewise for for this thing, right, it be some. Again, it slightly depends on your convention. But...
Yeah, and also you added the dissipative term.
Yes, the dissipative term. So basically, I mean, like you can work it out, right? So let's say, so yeah, because like in the pathing, coherent state path integral construction, right? Let's say the Lagrangian. Yeah, the way you get the Lagrangian is, it's. Yeah, I don't want to also like, let's say, enter this discussion, but let's say it's not really like the Lagrangian is in the classical mechanics-ish a bit, right? So this, so yeah, you have this kinetic or like this. Let's call it the time derivative term, right, minus the Hamiltonian. That's let's say that how you transform from Hamiltonian formalism to the action or Lagrangian formalism for in the coherent state formulation. I think that's, and it's the same for Majorana permanents, it's the same for non-relativistic bosons. Yes.
That what's that first I up on? No, there below. Below that.
A here?
No, and now to your right. To your right. Yes, that first I in that H. What's
There is no I.
an I? Okay, that's okay. So just
Sorry, my handwriting. All right. So before we go any further, there is, let's say, one thing that we might notice, right? I mean, already, let's say, in the, say, Dicke model Hamiltonian, right, is that, say, the dependence on the, so the interaction only depends on the combination of A and A dagger, right, the sum. So it is suggestive to go to a new basis, right? So rather, it is convenient to introduce new variables. So parameterize A as follows. So we have the real part, right, which will be this thing, plus the imaginary part. And so from this, right, it follows this. Phi is 1/2 square root of 2 complete naught, A plus A dagger. I is minus I A minus A dagger. Right? And this I'm trying to sort of show you all the steps. Too much, but so with this and following action. This part, I mean, it's the Majorana part is same first slide, but now you have your interaction term in a very nice form. I will explain what GT is in a second. We're almost there. Minus that. Bracket. Oh, all right. I'll write it down. Minus. Do you want me to write this down? Or like you can look at it. I mean, it's kind of bad. Right. And it's you know, it's nothing like hard, right? You just plug this into this, right, and work it out. Too many terms, and it's not the most illuminating expression. Where G tilde is simply H omega naught divided by n times G. And so we have 2 from here, and then we pick up, yes, we pick up essentially like another factors of omega, square root of omega naught from this, right, and square root of n from here. Now,
question. This is the usual Cavendish rotation, or is different?
no, it is different. Because I mean, here it's, yeah, like Cavendish rotation is, let's say, going from plus minus basis to classical quantum basis, right? Here we simply rotate the, let's say, both plus and minus branches of, like, so we just say parameterize our complex field A, right? So it's basically, it's the same as saying that Z is equal to X plus I Y, right? So it's simply this.
Sorry. First.
Oh, maybe.
This is square root of omega is equals to
Right, so omega naught, and then you would have, I think it's really squared. Okay. All right. I think that's it. This is very straightforward algebra. It's just... Okay. So let's say, are you happy with this action? All right, now let's do the 2pi. Right, so yesterday we all learned expression for the 2pi effective function, right? And now we just going to use it. Explain each ingredient. So the 2pi effective action takes the usual form. So what does it have? So it has, of course, your classical action, right? Then it has these terms. And I'll explain in a second, like what is D and what is G. And plus gamma. So D, the photon propagator, or let's say propagators, right? So we have D pi pi, right? D pi pi, D pi pi, D pi pi, right? In this, let's say, rotated basis, right? And then these guys are Majorana propagators. So, and gamma 2 equal to, again, for, I think it's nice to say, see this expression over and over again, right? Because then get more and more familiar with it. So it is the sum of all the two-particle irreducible with respect to dress propagators. connected vacuum diodes. Yes. So this is what Sandra demonstrated. So now, okay, I don't really expect you sort of to be able to transfer it, but let's discuss, right? So why you have a minus sign here, plus sign here? So why Majoranas come with a different sign? Yes, fermions. So remember, so like in some sense, like this part, right? Where did it come from? You remember? Remember Gaussian integral, right? We had a Gaussian integral. Exactly. So for remember that for yeah, so for bosons, right? So you have something like this. Right, so the result is proportional to one of the determinant, right? But for Dirac fermions, for instance, right? And this will be like the next part of the question. You have is the determinant instead. However, we see not spiral, yet we still have a half. What's the resolution? So here I claim that the 1/2 here stems from the square root of. But what about this? Right? We don't have a square root of for Dirac fermions. I think it's the answer is in the question. Don't have this for the Dirac fermions. Do we have Dirac fermions?
No, we have Majorana.
Yes, exactly. And for Majoranas, I mean, for maybe this. For those who don't know, you are about to know. Okay. Whatever, probably 1/2 something. It is actually Pfaffian of A, and Pfaffian of A is, well, it's a bit more complicated. Roughly speaking, it's a determinant. And so that's why we still have 1/2, but the sign is different, right? We will have this during the test. That's why the sign difference, but the prefactor is the same, right? And then we have the rest, which is the sum. I mean, this is the usual thing, right? So we have all the 2pi diagrams with just propagators, right? Any questions, comments, doubts? If not, okay. I think I can write this. Okay, so how do we get the equations of motion? Do you remember?
You look for the steady states.
Yes. I mean, because steady state in like, for open system, it means something different. Let's say stationary.
Yeah, it's stationary.
Yes, stationary condition, right? So essentially what you want is basically this. Right? I mean, and here phi means, well, but then this, right, essentially, and this. Right? And so you derived it yesterday, but maybe maybe you can do it. I mean, okay, I'll just write it down and then say. So here A means that it can be either phi or pi. It's sorry for this like bad notation, right? But it's so let's say phi1 is pi, phi2 is pi, right? I mean, so hopefully it's is equal to say minus of delta raised Okay, unfortunately, I erased the action, right? But I think you can, I mean, look in your action, right? And convince yourself that the only part of the only bare propagator, right, that depends on any mean field, or the inverse propagator that depends on any mean field, is the Majorana propagator, and it only depends on phi, right? Which makes sense because we had this coupling phi eta I x eta I z or some eta I y, right? Something like this. So that's why when taking the derivative, right? So this depends on phi. This does not depend on phi for obvious reasons. This does not depend on phi because there is no phi or pi in the bare inverse propagator or bare inverse photon propagator. Yeah, again, this cannot depend. This, yes, and then you have gamma 2, but yeah, yes, it also it will not depend on pi. Our approximation. Potentially. Okay, so now, at least in our approximation, this is. In principle, this everything, yes. So now we have this. Again, so I'll briefly explain. First of all, what is written here. And second of all, how you can obtain what is written here. So this, we take functional derivatives with respect to d, right? So what does this, so this does not depend on d, right? So what does this give us? Well, so you have a logarithm, right? So let's make it actually simpler. Logarithm of d, right? So what is the derivative of the logarithm?
Derivative of d divided by d, no, 1 divided by d, versus d.
We have, right? Good. Next one, this one, right? Oh, this one is simple. Say. This one is simple, right? Because this get this, right? And this is linear in these words. Simple. Finally, we have this. And what is this? Remember, we defined the so-called proper self-energy, right? By a derivative of this remaining part, gamma 2, when you cut one of the lines, right? So this is cutting the line, but we define it with 2i prefactor, right? So this is, okay, so this is, let's do some advanced math. This. And then you should get minus, right? Minus I half, if I'm not mistaken. And that's it. So that's what we have, right? So we have, and then you can already like cancel all the, I halves, right? And then what we end up with is this plus this minus this, no, this. And then what you have is you you go, yeah, as this with the right hand side, multiply everything from the right by D. This is exactly this, right? So here, I mean, it's just, let's say it's a full matrix multiplication, right? So all the indices, all the times, right? So what I mean by this is, let's say, FG, let's say T prime, simply means D, let's say S, right? TS. So it's a simple convolution, right? So let's say matrix multiplication in the time domain, right? But yeah, but you see that, you know, from like in what, like 4 steps, we got a Dyson equation, right? And I mean, I think it's not too surprising that the Majorana part like works absolutely analogously. Here it's just all the possible indices, right? So say so Majorana simply has more indices to it, right? So the alpha, beta, you know, IJ stuff. And so are there any questions to this point, or is it like clear? This is something that you've done yesterday. I mean, you did yesterday, right? In principle, we would also have this here. But like, we will not actually have it. That's why I think if you want to be like very general. Yes. And remember, so essentially what Aleksandr showed you, yes. By the way, yes, so this is say the photon cell energy. This is the Majorana. That is certainly currently sorry. Okay, in case I mean, like you're very like silent, right? It can only mean 2 things. Either this is like very clear, or it's absolutely not clear. Which one is it? Or is it? I mean, come on, right? You know which one is it? But this is, yeah, I mean, like, let's say, like, if I rewrite it sort of like this, right? I mean, this is the Dyson equation, right? So it's the, you know, the usual thing. The D is what? Oh, now it's really advanced. Do I dare to attempt it? So it's like, okay, I'll read diagrammatically. That's, you know, like the full plate equal to square plate plus, how was it? No, let's make it like full plate like this. Is it from the left or from the right? The subelement.
So the
Yeah. Right. So this is simply this, right? Thing it's just written in a, let's say, more convoluted fashion, but like at the end of the day, it's just the Dyson equation, right? And then we will, again, you already saw it, but you can massage it such that you end up with 2, I mean, in this case, for each of them, right? So 2 equations, one for the statistical function, one for the spectral function, and then you not on the contour anymore, and then you plug the system of equations in your computer and you solve them, right? So we essentially we take the same strategy, and this is the first step. All right.
So I'm a little bit confused. So there will how because the Dyson string equations are like decoupled, right? From the Poisson and the Majorandas. How they talk between them.
They talk via this. So this will depend also on E.
So there is more than an additional equation for the two self-energy of
Yeah. So I mean, it's like, let's say at this point, this is exact, right? So if you somehow miraculously was able to take into account all the diagrams, this would be exact. But then you actually do truncation, right? And then your truncation sort of gives you the form of this object in terms of the propagators.
Yeah, because I think of this because you can write a string relation equation without doing all the steps, and you will get the same equation that is there. So yeah, my point is, what is how do you will connect those?
I mean, we will later do approximation, right? So we will later select diagrams that we sort of keep. For them, we will derive sigma and pi, right? And so then we will have this closed system of equations, so on.
And the direction wouldn't be not better to sum all the Majorandas because
Sorry?
To instead of working with the energy of a single Majorana would not be better to sum all the self energies of the Majorandas and have a single field for all the Majoranas because at the end they are decoupled. So
What decoupled?
the Majoranas in the model they their spins. The spins they don't interact between each other.
Okay.
So will not be more easy.
I mean, no. But I mean, at the end of the day, they still do interact with each other, right? Because you have a term that couples.
Yeah, but at second order.
Yeah, but I mean, we will, go to at the very least, let's say second order, right? So we will, once you include interactions, they become coupled to each other, right? So, yeah. All right. This should be it. But I cannot not comment on this stuff. This is Dyson equation, not the Schwinger-Dyson equation. Schwinger-Dyson equation sounds like Dyson is credited alone for this usually. Okay, so again, here, right? So again, in this matrix multiplication, you also have, let's say, if you work in plus minus basis, right? You also have, plus and minus and all this, right? In principle, you can proceed working in this plus minus basis, and this is, let's say, I think for, let's say, deriving the structure of the Kadanoff-Bain equations or the Dyson equations on the, it's a bit more convenient to switch to the Keldysh basis, right? So to perform Keldysh rotation. So, in my opinion, it is convenient. But again, you can do it however you like, right? You may want to stick with plus minus basis. You may want to work on the contour and then do this decomposition as Aleksandr did yesterday, right? So it's whatever you find most convenient, right? But I feel that it is convenient to perform the Keldysh rotation. Which is, okay, and I'm sorry, but I use a slightly different convention. But, so you were using with square roots of 2 and all this, right? I use slightly different one. So in which basically this is this. This is it's right? And it's very easy to find the connection to like what was in the lecture. All right, and then let's derive one of the equations, let's say in some level of detail. What can I erase? I think I can erase this, right? Thanks. Because this I would like to keep. Right? Okay. No one is protesting. It's fine. So, all right. So let's choose one of the equations. This kind. So in the matrix form, here's what we have. Quantum classical. So here, note that the only, because remember the interaction, right, involved only the real photon field, right, so phi component, right? Thereby, sort of, you only have the phi component of your self-energy, right? So there is no phi pi, phi, right? So this is the only one that is non-zero. Here, so this is, I'm simply writing this part now, right? Then have phi, quantum classical. And what I essentially do, I compute sort of the, so that one of the indices is quantum, and one of the indices I think is classical, yeah, and one is classical, right? So A quantum, B classical, right? And then sort of in this, and then you still have this phi multiplication, right? And this is what I'm writing, right? That fix this, but then you still have other indices that you need to say multiply. Phi, quantum classical, right? So far, so good, I think. Phi, quantum classical. Then you have this convolution, right? And then here you have, of course, just phi. And then because I fixed this to classical, B classical, right? So the other index is classical, and here you have classical, right? So classical, and B is classical. Phi, classical, D, phi, classical. So is this it? Or do we have something else? So remember, A is quantum, B is classical, right? And then you have, you know, so let's say it's like this. A, quantum, let's say C, sum over C, I'm very explicit here. B, C, classical, right? So do we have another term? Right, so here we have classical, right? So C is classical. Is there another one? So C goes from, okay. C is quantum classical. Right? Okay, so there is also, there needs to be like another term, which is where C is quantum, right? So in the matrix multiplication, right? I think I really lost too much here. But okay. Okay, so we have very similar structure. Okay, so here again, there's an exercise. Convince yourself that, sorry. Quantum, that's fine, of course. Convince yourself that only the diagonal entries have a quantum component. Off diagonal plots do not have it. of the Baire propagator, of the Baire inverse propagator. Quantum, right? And then again, you multiply it now by what? Again, B is fixed to classical, but C is now quantum, right? So you multiply by quantum classical. So again, D phi phi, D phi phi, D phi phi, D phi phi, quantum classical, 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 quantum classical. Everything is equal to 0, right? So this is our equation in the matrix form, one of the equations in the matrix form. Right? Well, it's actually 4 equations, right? In the matrix form. So let's take one of them. Let's take which one did I take? Yeah, the phi phi component. So like you multiply these 2 matrices, right? And you get again a 2 by 2 matrix. And let's take the result, which is the the phi phi component, right? So the upper right, upper left corner. And in the upper left corner, if you multiply, so again, let's do it slowly together. You know the rule, right? Sort of it's like this sausage thing times this sausage thing, this sausage thing times this thing. Or yeah, this row by these columns. So then you have phi phi quantum classical, phi phi classical minus phi phi quantum classical equal phi classical plus we're almost there. Phi quantum quantum classical phi minus sigma phi quantum quantum classical phi phi. It's all right. Good. So what are these guys? What are these objects?
Photopropagator, the Baire photopropagator.
The Baire inverse photopropagator.
Oh,
exactly.
yeah, that is a man.
Yes. How can you get it?
From the classical equation of motion.
From the classical action.
Yes.
Yes. So one way is, yeah, so basically you look at the quadratic part of your classical action, right? Remember? And sort of like, let's say one way to do it is, I mean, let's say, in an algebraic manner, you can express this by where, okay, this is, let's say, second function derivative. But again, sort of like this is more like this is a slightly fancy way to express the fact that you just look at the quadratic part of your action, right? So let's say phi, phi, right? This is essentially related to, this would be like I times d naught minus 1 by phi, right? This is just, you know, because like if you take the, because if you take the derivative, right, that's it, right? So my claim is, you convince yourself, because also this is, yeah, because I derive the equation slightly differently, like for actual, let's say, purposes research. So And I think, yeah, this result is also correct. I'll check it. The inverse propagators. Read. So like the relevant ones, right? By the way, when do we make the break? 12, right?
Technically, 40 minutes.
Okay. All right, so we have this, right? Go squared. Then we have this. Okay, and here it's a little bit like a matter of taste. So I personally prefer to sort of like to express this as some like differential operator, right? But instead you can also sort of have a time derivative of your delta function, right? So, and then it's sort of like some in a distributional sense, right? But sort of the idea here is that this acts, let's say, on the right, right, with the time derivative. This somehow clear? Well, I see no complaints, but not sure what to make of it. But yeah, I mean, finally, the 1.5 is kappa. All right. Exercise. Show it. So now, I think I can erase this part. So now if we just plug this in, what we end up with, following. So now we simply plug this into this, and we end up with following equation. Classical, phi. I'm going to be extremely explicit here. Minus squared. It's the other. Kappa. So here we already see, like, you know, the damping, right? So we are on the right track. Right? Plus I omega naught kappa E quantum classical I fine. And finally the memory kernels. But this looks familiar, right? So this is something that you saw yesterday, albeit in a slightly different form, but we will also most likely, yes, we will convert this to a very familiar in a second.
I believe that the square cannot be the omega square because by units doesn't match.
No, it does match because phi and pi, if you wish, have different dimensions. And pi and pi have different dimensions. So because the way we define them, if you remember, let me again briefly remind you, was that phi is 1/2 omega naught sum O, right? Whereas pi was omega naught
Okay.
up. So you see there is a discrepancy in the dimensions, so that's why. Okay, this is what I call marker. Now, to bring this to a more, let's say, familiar language, I can erase this, right? So remember yesterday, Alexandra showed you that, yeah, the two more the types of Green's functions, right? So the statistical and the spectral propagators. And yeah, and so they are connected to this to this classical and quantum to like propagators in this classical quantum basis as follows. And you can first, let's say, check it, convince yourself that, by the way, also I apologize that in my convention and Jamir's convention probably differed by ice, right? So like what he introduced as a propagator is probably I times what I call a propagator for minus I or something like this. But this is, yeah, this is exactly what Aleksandr introduced yesterday. The minus is prime. Quantum classical is I rho prime theta t. Right, so essentially one is the, so this is the basically the retarded propagator, this is the advanced propagator, right? Now F is simply the classical, right? And then the decomposition of the likewise. So the classical quantum self-energy can be decomposed into local part first plus I sigma rho. This thing sigma quantum classical. Okay, I think it's no surprise that it's very similar. Right, and finally, sigma quantum is nothing but sigma f from yesterday. Right? So now, if you plug this in to this, what you end up with is the following. Or now it's pi, right? So it's the, sorry, phi f pi. So the statistical propagator component pi. This, okay, I'll in a second. Finally, memory kernels. Just, I mean, it's like you saw them yesterday. Again, this should be familiar somehow. Yes, by now. All right. Well, I mean, we will not have this correction, but let's keep general. Sigma squared t is nothing but omega squared t plus sigma naught phi. So it's so like it's the tadpole contribution or the lamp shift or okay. So we made it. So we have one of the equations, one of the two PI equations, one of the Cardano-Flame equations for the Dicke model, right? So now all you have to do is get derive 3 more for F, 4 more for rho, then and then the same for Majoranas, and then for the photon mean field. But then you're done. Then we will select diagrams, compute the self-energies, discuss how to do this numerically. But then, yeah, I mean, then basically you almost have your code. Are there any questions? I think, yeah, I should, let's say, I'm not sure if we should go on a break, but at the very least, let's take a mental break. Questions?
I have one stuff. So why you use the Martin, is there a special thing? So if you have a lot of spins, why don't you use like the spin current state or something like that? This is spin computation or is more complicated?
What you call spin, what? Yeah, spin coherency. I mean, this was like my first, let's say, said that, okay, it might seem tempting to formulate in terms of spin coherent state path integral, but then you have this thing. Okay, in our case, it would be 1 or minus, let's say, thing hanging around. And this is annoying. So this would be in our path integral. So we would have to impose this constraint somehow. Basically, the point of the Majorana map is that it does it for you. Otherwise, you can impose this somehow. Let's say like via some, like you can.
Yeah, that will give you an additional field like that.
You can, in principle, formulate it and then sort of add some bit to your action and so on and so forth. But then, like, you can imagine that what this gives you to your actions, right? So this, so that's sort of like the reason why people use this auxiliary degrees of freedom instead of working directly with spin sometimes, right? So again, it's, there is like no free lunch, right? So like let's say each approach has its own like benefits and weaknesses.
It's like more geometrically clear that in the
Yes.
case.
But I have to admit, okay, it's not that I've checked like all the papers in the world, but I have never seen, I think, people working like with spin coherent path integrals like in non-equilibrium, non-equilibrium setups. I only saw it like in equilibrium, but I might be very wrong here. But that's.
By the way, this that was mentioning, it's probably convenient if you want to make contact with the classical limit. So
Well, yeah.
The constraint goes.
Yes.
And goes to infinity, so you don't have any more. And so,
but then, yeah, you can also then sort of, but yeah, so like you can also do, for instance, Holstein-Primakov then as well, right? So it's sort of like, again, if you do something semi-classical, I think it doesn't really matter like which map. Exactly. It's like, it's a very like straightforward way to like semi-classics, right? So I wouldn't say that like it's a big advantage compared to other maps, right? Yes.
Should probably have asked this 2 days ago.
Okay.
And it might be very trivial that you have done those operators that are indexed as quantum or classical.
Yes.
And have more or less been able to get along the algebra. But what is that there is quantum and classical about each label?
Yeah. So classical, right? I mean, already sort of, I guess. Okay, let's say you have all classical, right? Some operator, all plus plus, all minus. And then you have all quantum, all plus minus, all minus, right? which one can have an expectation in the absence of, let's say, funny sources, right? So that like break some probability conservation, something like this, right? So let's say which one can have an expectation?
The class.
Yes, so the classical one is the one that, if you wish, has expectation values and, let's say, like on its own, sort of like observable, say, implications. Well, probably not the nice way to formulate it. But yeah, sort of like the classical one has expectation value. The classical propagator, remember, it knows about how, let's say, occupation numbers of your system, right? So let's say it's the one that is related to things like occupation number, or if you wish, density, things like this. The quantum component by itself, right? So it's always, you need to mix it with classical something to have something non-zero on the, as an expectation value. And it knows about, let's say, spectral properties and things like this, right? So in some sense, yeah, and it's also, yeah, so let's say like the classical one it's called classical because it's like closely related. Let's say because if you drop all the quantum fluctuations, this is what got it, right? So the classical equations are like, right? Then this is, say, when you include fluctuations in some sense, right? And in particular, also remember that if this is, by the way, like this, I think it's a nice comment here. So let's say you have pi to the 4th. Then, if you go to classical quantum basis, right, the interactions would take form. One is going to be like this. One is going to be like this. So let's say there is one way to argue that in a lot of cases, this one is more important than this one. If you neglect this one, then the remaining action, I mean, again, sort of, there will be at most like quadratic in by quantum. And remember that then you have this trick that Jamir showed you, how you can reformulate this as a Langevin equation, right? So basically, but Langevin is not quantum. Like Langevin is, let's say, it's a stochastic equation, right? So it's like classical fluctuations, right? So if you sort of neglect higher order quantum fluctuations, right, then you have a semi-classical description, right? So again, only if you really capture like these very quantum terms, you get access to like full quantum fluctuations, right? So actually, if you neglect this, what you get is the so-called truncated Wigner approximation. So it's like I mean, some of you might be familiar with this, right? So this is how you get it from the Schindler-Schrommers. And so, and then like, to go even more quantum, you need to take like, all these quantum terms. That's why it's like, these quantum terms, they control quantum fluctuations. Classical is, the one that survives in the classical limit. So that's why. Yes.
Just one last question. The difference between quantum and classical fluctuations is the coherence. Is it?
I mean, the way I like to think about, well, yes. Okay, let's say from the way I like to think about it. I mean, maybe it's, so let's say you have some fluctuation dissipation theorem. Then you would have something like this. Maybe plus 1 half. Let's say plus 1 half. Rho. So this is FDR. So this is what I call this a classical fluctuation. Oh, no, not classical. Let's call it statistical. Statistical fluctuation. And then you have this quantum on top. This is what I call the quantum. in certain limits, when you have large occupancies, you can make like this thing. This translates to this. Right, so this is, well, I mean, maybe it's not like the best terminology and so on, but this is how you can properly think about it. I mean, okay, this is how it is, I think. Like, I like this language of the occupancies, FDR type of thinking. Of course, it's like, it's, you know, as was explained yesterday, it doesn't really call out of equilibrium in general.
But I can also think about it as the question about period states. Is that like you have a
Yes, I think then sort of like, yeah, so let's say the classical factor are like the diagonal properly like entries, right? And then you like you have coherences, right? Now this is like really flat, right? I think that's also like a good way to think about it. Please. Would you please remind me of the Hamiltonian that we're working on? Yes, of course.
It's in the dark side of the board.
Of course, it's sometimes sort of like, you know, it's hard to see, how do you say, hard to see the trees behind the forest, right, or something like this. With all this, right, it's the original model gets obscured. So what we are working with is the Dicke Hamiltonian, which is a boson spin boson model. We have photons, bosons are the role of bosons is played by photons in the cavity. But your spin, which is you can think of as an ensemble of two-level atoms. N of them, and they are coupled via essentially a dipole type of interaction. This is the model. And this is the equation that you get after a couple of steps. And then we have plus tolerances. Any further questions? Like 2PI in general, or?
I just want
Yes.
to curiosity. For example, yesterday today was mentioned that you constructed the linear system of your equations and then use a computer to solve the system. The difficulty is with the number of spins you have, or
I will come to this later. So that, like, let's say, but already now, let's say the advantage is the complexity as far as like the system volume goes, right? I mean, it's basically like it scales like polynomially, right? So as opposed to, let's say, if you have like a full, like if you want to do exact diagonalization, right? So it goes exponentially, the Hilbert space, blah, blah, blah. So here it's polynomial, which already tells you that, of course, like, let's say, on a quantitative side, it often cannot compete with like these exact methods, right? There is, again, like if you have something that can be solved polynomially, right? If this was like as accurate as, let's say, these exact diagonalization methods, or let's say tensor networks and so on, like, you know, everyone would probably switch to 2PI. So it has, but yeah, that's one of the biggest advantages that it's not very sensitive to the systems. It's a question. Would you mind also give the 1 in 5 on Majorana presentation? I probably would. Guess I wouldn't. By the way, but while I'm doing this, right, I can go to lunch. Here's one question that I sort of suggest you to think about. So remember, we were talking a lot about Markovianity, right? Sort of this Markov approximation, right? And now you have memory kernels. Does it look Markov to you?
Mhm.
So what's the, where's the catch? Just you think about it. All right. Minus. Could have probably already let that go on the like lunch break, but it's give me like a company, I guess. Okay. Submit. And G tilde is, I think this is it. I don't, yeah, I think that's it. G tilde is. I think that should, it is Markov with the boss, but not interaction between particles in the system, maybe. Yeah, I think we can maybe, yeah, so discuss this a bit more if you want after, say, the lunch break, right? So this, I think, I mean, it's, I think it's not a trivial question. So think about it. All right, so I suggest, yeah, we finish here, right? And we continue. Let me check. Yeah, I think let's then continue.
Okay, nobody move. We're gonna do the group picture. So let me don't leave the room.
Nobody.